All right, people, I'm here to talk to you about AC power and transformers. And before we can talk too much about them, we need to talk about the original power plants that Thomas Edison built. The original power plants that Thomas Edison built were DC. They were direct current power plants, which were basically like big batteries, okay? And there was a problem with this. When you have a DC power plant, and here's the power lines, and we have lines right here, then power lines have to run all the way to the buildings with all the people in New York and the big cities, okay? And then they have to come all the way back to the power plant. So have a full circuit, all right? Now, we know that V equals IR, and that's Ohm's law. Well, DC power plants had a real problem, and that problem was resistance. Because electrons had to actually leave the power plant and travel all the way through the buildings and travel all the way back. So one electron had to make this entire trip. What happened was the wires got hot and the electricity couldn't go very far. So he had to build another power plant and do some more buildings, and then another power plant and do some more buildings, and then another. He had to build a power plant in crowded areas just every few miles, so that was terrible. So a guy who was very, very smart named Tesla said, we're going to use AC power, okay? An alternating current. And this is what's going to alternating current. This is what's going to be based on. We're going to say, we know the power plant can do so much work, that's power, and we know power is equal to current times voltage. He said, what I'm going to do is I am going to raise the voltage and lower the current, because the current is the problem. The current is what is creating the resistance. This needs to be changed, all right? The current was having too high a current with V equals IR was creating a lot of resistance. So what are we going to do here? Here's what Tesla did. Tesla said, hey, if we can have an alternating current, a current that goes back and forth, right? We can take it and we can attach it to a big, doesn't have to be big, we can attach it to a chunk of metal like this that is called soft iron. And all that means is iron that is very easily influenced by a magnetic field. I'm going to take a wire with an AC current and I'm going to wrap it, all right, around this metal, and I'm going to run a current through it. Now, we know that this is a tall, thin coil, so this technically would be a solenoid, but we'll call it a coil here. As the electricity goes through here, we think about the right-hand rule. As electricity is going in this direction, we would end up with a magnetic field moving through this coil with a north down here and a south down here. But since we're using AC current, just a second later, the current's going the other way. So now it would flip-flop and the north would be up here and the south would be down here. So now if we have an AC current, we know that a magnetic field is moving forward and backwards through this coil. It's no different than moving a magnet past the coil. What happens if you move a magnet past the coil? Well, you create a current. Now look, this is all one piece of iron. So if a magnetic field is moving back and forth here, a magnetic field is also moving back and forth here on this side. The north and the south are switching. North and south are switching because the current's switching back and forth. So if we went over on this side and we put many more wraps, then we'll still have the same amount of power on this side, but having more wraps increases the voltage. let's say we had 1,000 wraps on this side and 5,000 wraps on this side. Well, then the voltage will go up by 5 times. Now let's pretend that we're powering a 60-watt light bulb. So we're going to say 60 watts of power is equal to a certain current at 120 volts. So the first thing I would say is, what current is running through this wire? And you would say, Mr. Perkins, that is 0.5 amps. Just use P is equal to IV. On this side, since we have 5 times as many wraps, then we have 5 times the voltage. 5 times 120, there's 600 volts on this side. We still have 60 watts of work being done, or 60 watts of power. What is the current on this side? The current on this side is 0.1 amps. So by making the voltage 5 times higher, we've made the amperage 5 times lower. And therefore, this side now has high voltage and low amperage, and therefore resistance, or the ohms, aren't a problem. So we take this high voltage side, and now we can run electricity for a very, 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 very long way. Hundreds and hundreds of miles. If this is the power plant, and it creates power, and we create high voltage here, the high voltage means there's low current. So the electricity will run for miles and miles and miles. Then if you want to, let's say you're hundreds of miles away and you want to hook your house up to the high voltage power lines, what would you do? You would just build this thing backwards. What does that mean? You would be attached to the power lines, the high voltage over here, they would have more wraps. High voltage. And then when your house is over here, you are going to attach this and you're only going to put a few wraps so that you only get the volts that you want to come to your house. This was Tesla's genius idea. When the voltage goes down, that's called a step-down transformer. When the voltage goes up, like this, that's called a step-up transformer. All right, let me give you one problem, then we're going to be done with this transistor talk. Here's a transistor. It is made of soft iron. On this side, you are plugged into the wall. So you have 120 volts. And you are going to be charging your phone, so we're using 5 watts of power. All right? P is equal to IV. What is the current running through this wire? All right, let's solve it. 5 watts is equal to some current times 120 volts. I'm sorry, this is supposed to be a V. All right, 120 volts. 5 divided by 120 is going to give you a very low number. 5 divided by 120, you're going to be using 0.04 amps. 0.04 amps. Now, on this side, we want to plug a 12-volt battery charger in. If there's 1,000 wraps on this side, how are we going to step it down to 12 volts on this side? That's right, we're going to change the number of wraps. If we're going to step it down to 12 volts, How many wraps do we need on this side? Yep, 100 wraps. 100 wraps. We have 1/10 the wraps. We have 1/10 the voltage. So now we have 12 volts on this side. It's still using 5 watts of power. P is equal to IV. What is the current right here going to your little phone charger or whatever it is you're using? You would say, okay, 5 watts of power and 12 volts. 5 divided by 12. 5 divided by 12 equals, guess what? 0.4 amps. So if you have 1/10 the voltage, then you're going to have 10 times the current. And now you can use this current to charge your phone or charge whatever you want to charge. That's how a transformer works. Last question, is this transformer a step up or step down transformer? That's right, this one is a step down transformer. Last question again, what formula do we use when we're calculating the voltage across a transformer? P equals IV. All right, great job.